Hey guys, welcome back to another lesson for the SOA's Statistics for Risk Modeling exam. Today's video covers mean squared error, or MSE for short. MSE is a fundamental concept in statistics. Alright, so let's paint a picture. Imagine you are an actuary. You have the power to predict the future. Well, sort of. Instead of a crystal ball, you have data. Let's say you're trying to figure out how much the insurance company is going to have to pay out for car accidents next year based on the age of the drivers. You have your data points. These represent real claims from the past. And you have your model, which is this fancy line right here, trying to predict where those points fall. But looking at this, some of these guesses are pretty terrible, right? We need a way to score how wrong we are. This is where the mean squared error, or MSE, can help us. So why do we use it? Well, we take the distance between what actually happened and what we thought would happen, that's the error, and we square it. Visualizing it helps. See these squares popping up? By squaring the error, we are basically punishing the model for making big mistakes. A tiny miss? Whatever. But a big miss? The square of a big number is like way bigger. The MSE quantifies accuracy by averaging these squared differences. Okay, time for the math. Don't run away, it's actually pretty simple. Here is the formula. So let's break this down. N is just how many observations, or claims, we have. Y sub I is what actually happened. And this F with the hat, yes, it's actually called a hat, that's just our predicted value on the estimation line. We take the difference, square it, sum them all up, and divide by n. We're literally just finding the average of the squared screw-ups. A smaller MSE means higher accuracy. A larger MSE means, well, time to find a new hat. Now, there is one tiny gotcha I need to mention. You might look at this and say, hey, in my stats class, we divided by n-1, or n-p. Well, that's just what happens when you have formulas from different source readings. The general MSE formula is from ISLR and applies more generally to modeling methods. For least squares regression, or hypothesis testing, which mainly comes from the Freeze textbook, we need to tweak the bottom part to make it an unbiased estimator. Basically, the math gets fancy to account for the degrees of freedom used up by the model. We'll cover that in another video. But for the general MSE we are talking about here, we stick with 1 over n. It's biased, but who's not these days? So let's look at a concrete example of how the MSE is actually calculated, because numbers are where the magic happens, like pulling a rabbit out of a hat. Without the rabbit. We still have the hat. Here's the question. Calculate the MSE for the following data. We have 5 observations, and we are given the actual values and the predicted values. Looking at the table here, we have 5 rows, so n equals 5. Easy peasy. Now we have to calculate the squared errors for each individual point. This is the part where we find out how wrong our model was. Observation 1. The real value was 3. We predicted 2.5. The difference is 0.5. Square that bad boy, you get 0.25. Similar error for observation 2. Observation 3 was a bit of a mess. We were off by 0.8. Square that and we get 0.64. Yikes. We do that for the rest of them. Bam, bam. And we get this list of squared errors. Now we sum up these bad boys to get the sum of squared errors to get 1.48. Finally, to get the mean squared error, we divide that sum by our number of observations, 5. Now, quick side note, because this trips people up all the time. We are dividing by n here, not n-1. The question didn't specify how the estimation function f hat was calculated. So 1.48 divided by 5 gives us 0.296. And there you have it. That is our mean squared error. Alright, so let's talk about the difference between training data and test data. Imagine you're studying for exam SRM. You have a textbook full of practice problems with the answers in the back. That is your training data. You use it to learn the patterns. But then on exam day, after getting close to no sleep due to crippling anxiety, running on pure adrenaline and caffeine, you drive 2 hours to the nearest Prometric center, start the exam, and realize you're completely f***ed. You haven't seen the questions before. That, ladies and gentlemen, is your test data. If you just memorized the answers to the practice problems without understanding the math, you are gonna fail that exam. Hard. We want our model to work on the exam, not just the practice problems. That's why, when studying for exam SRM, you should focus on understanding the material, not just memorizing the answers. Typically, we care most about the accuracy of our predictions on unseen data. So assume we fit our training data, this set of x and y's here, and we get our estimate, f hat, and our predicted values. Here is the catch. We are typically not interested in whether our prediction is close to the real value for the training data. We already know the answers when we're training, so what's the point in creating a prediction model that's only going to be used to predict answers we already know? What we really care about is whether f hat of x0 is close to y0, where this x0, y0 pair represents a brand new, unseen test observation. So mathematically, our goal is to select the method that minimizes the test MSE. That is, the average squared difference between the actual new value and our prediction. In the real world, separate test data is usually not available. The SOA isn't going to give you the questions before the exam. We could try to minimize the training MSE instead, but that often leads to overconfidence. There is hope. We use a technique called cross-validation to estimate this test MSE using only our training data. We'll cover that in another video. So far, we've talked about MSE for regression, but now, let's talk about classification. The goal of classification is to assign qualitative labels to observations. One aspect of evaluating classification models is understanding their error rates. The error rate measures the proportion of predictions the model got wrong. Mathematically, we define the classification training error as this function right here. Let's break it down. The formula is conceptually similar to the MSE formula for regression. First, we have n, the number of observations. Next is y sub I, that is the true label of the observation. And then y hat sub I, that's the predicted label. Capital I is the indicator variable or function. It looks at the condition inside. Is the real label y different from our guess y hat? If they are different, meaning the model was wrong, the function spits out a 1. But if they match and the model was right, it spits out a 0. So we just add up all the ones, all the mistakes, and divide by n. That gets us the error rate. The reason we assign a 1 to mistakes rather than 0 to mistakes is because, similar to the MSE, we want to minimize the error, so we want a function that counts the mistakes, not the correct predictions. Similar to the test MSE, we can express the test error rate as the formula on the screen. Since we covered the details of the test MSE earlier, we'll skip the details of the test error formula here. Thanks for watching. For a comprehensive written course, hundreds of practice problems, progress tracking, and AI-assisted tools, visit the Actuarial Nexus. See you in the next lesson.